This is lecture 5 on half-wave rectifier with now RC load. So the circuit diagram would be an AC source connected to a diode, then the diode is connected to a resistive load, and there is a capacitor in parallel with the resistor. So the source voltage is V maximum sine omega t, and this can be expressed in this graph, where this is t the period, this is half of the period, this is V maximum, and the voltage change in the sinusoidal fashion. So now I will draw the voltage waveform across the load. So V output. So V output will look like this, and then during the first mode, called mode number 1, the diode is on, meaning that the diode current is greater than 0, or we can say the diode current, which is the current that is moving through the diode, is equal to the capacitor current plus the resistor current. So it will be IC plus IR is greater than 0. At this mode, the output voltage across the load is equal to the input voltage is equal to the capacitive voltage, or the output voltage. So this all equal to V maximum sine omega t. Now from here, the current that is moving through the capacitor here is actually equal to C dVc over dt plus the resistor voltage is simply the output voltage divided by the resistor, which is greater than 0. Now I will put this instead of this and this, so I will get d by dt multiplied by c multiplied by V maximum sine omega t plus V maximum sine omega t divided by R, which is greater than 0. When the voltage across the capacitor reaches a certain value in such a way that the capacitor voltage is greater than the diode voltage, the input voltage, then the diode will turns off, because the voltage here is much higher than the voltage here. So the diode will turn off, and the diode will turn off at an angle, let's say it's theta. So then the current that is drawn by the load will be coming from the capacitor due to the energy storage in the capacitor. So the voltage will go down until the next cycle, where the voltage of the source, this voltage, is greater than the voltage across the capacitor. Then the diode will turn on again, and then it will repeat with the frequency of the supply. So this is T, so I can write it in this way. At this angle we call it alpha plus pi, which is the angle at which the diode will turn on again on the second period. So now at omega t equal to theta, and theta is the angle at which the diode will turns off. So we replace omega t by theta. Before we substitute theta into the equation, we will find the derivative of this one, and we will get C omega V maximum cosine omega t plus V maximum sine omega t over r greater than 0. So at omega t equal to theta, the current will be equal to 0. So C omega V maximum cosine, instead of omega t we put theta, plus V maximum sine theta over r is equal to 0. So at theta the currents will be equal to 0, so the diode will turn off. Now divide both sides by cosine theta, so you'll get C omega V maximum cosine theta over cosine theta plus V maximum sine theta over r cosine theta is equal to 0. So we will get C omega V maximum, this is 1, plus V maximum, this is sine over cosine is tan theta equal to 0. Finally we take the V maximum common factor, we will get and divide multiplied by r to both sides, so we will multiply, I forgot to put over r here, so we multiply both sides by r and take Vm as a common factor, so we will get V maximum Cr omega plus tan theta equal to 0. So tan theta is equal to Cr omega in negative sign, so theta will equal to tan inverse minus Cr omega. So this is how we can find the angle at which the diode will turn off and the capacitor will start to discharge on the load. To find it on the calculator, we simply put pi minus tan inverse Cr omega, and it turns out that theta is in between 90 degree pi over 2 and less than pi 180 degree, and when our C omega is very large or greater, then theta will equal to 90 degrees or pi over 2. So now at the end of this mode, VC is equal to V output is equal to V maximum sine theta. So as we said in the graph here, that at theta the voltage that is across the resistor is actually equal to the voltage across the capacitor, and this voltage is equal to V maximum sine theta. So this is like the initial value voltage across the capacitor, and we need this in the second mode. So mode 2 is when the diode is off, and when the diode is off it simply acts as an open switch, and the capacitor will start to discharge into the resistor. So IC here is equal to IR. So IC plus IR is equal to 0. IC is C dVC over dt, plus IR is V output over R, which is equal to 0. We know that our initial condition is VC is equal to V maximum sine theta from mode number 1. So now we have this first order differential equation and we have to solve it. So to solve this differential equation, we simply say dVC over V output plus 1 over RC multiplied by dt equal to 0. So taking the integral for both sides, and we get natural logarithm of VC minus V out plus 1 over RC multiplied by t equal to 0. So now taking is equal to ln VC over ln of V output plus 1 over RC t equal to 0. So taking exponential function to both terms of the equation here, we get e to the ln will go with the, so the ln will goes with the exponential function. We will get VC over V output equal to minus 1 over R. We will get e to the power minus 1 over RC multiplied by t. So VC is equal to V output e minus 1 over RC t, and we know that V output is equal to V maximum sine theta. So we will get VC equal to V maximum sine theta e minus t over tau, and tau is equal to RC, which is the time constant. So now if we want to express VC as a function of omega t, this is as a function of t, we simply put V maximum sine theta E minus omega t minus theta over tau multiplied by omega. The diode will remain, diode D will remain off till V input is greater than Vc. Vn is known as V maximum sine omega t, should be greater than V maximum sine theta E minus omega t minus theta divided by tau omega, which is this one. Diode will remain off till this input voltage is greater than this voltage. When this condition occurs, meaning that the diode will turn on again. So diode D will turn on when omega t is equal to 2 pi plus alpha. And in graph I showed it to you earlier that it's gonna be this, which is 2 pi plus alpha. And if I draw on this same graph the source voltage waveform, it's gonna be like that. So this is 2 pi, so this is alpha, which is when the input voltage is higher than the capacitor voltage on the that appears on the output. So V maximum sine, we said V maximum sine omega t is greater than V maximum sine theta E minus omega t minus theta over tau omega. So V maximum sine, I will put this instead of omega t, so I will get 2 pi plus alpha, and this goes to the other side, so minus V maximum sine theta E minus 2 pi plus alpha minus theta divided by, now V maximum will go with V maximum. I will only have sine, and 2 pi will go, and alpha is left, so minus sine theta E to the power 2 pi plus alpha minus theta over RC omega, I missed the omega here, is equal to 0. So this is used to find alpha, and it only can be found using numerical solution. So to summarize, the output voltage of this circuit, it will be V maximum sine omega t when omega t is greater than 0, less than theta, and then it's V maximum sine theta E minus omega t minus theta divided by omega tau when omega t is greater than theta and less than 2 pi plus alpha. If I want to find the current that is flowing in this circuit, just a reminder, theta can be found by subtracting pi using tan inverse RC omega. So to find the current that is flowing through the capacitor IC is equal to C dVc over dt, and I will take simply the derivative of this since Vc is equal to V output. So I will get C omega V maximum cosine omega t at omega t greater than 0 less than theta, and then I will get minus V maximum sine theta divided by R E minus omega t minus theta divided by RC omega. This happens on omega t greater than 2 pi plus alpha and less than 2 pi plus theta. And here I can say from theta up to 2 pi plus alpha. And this can be the same as the previous one. So now let's take a look at the diode current. The diode current is simply equal to the source current. Since we have the circuit in this way, it's always that the source current is equal to the diode current. So how to calculate this? During D is off, the diode current and the source current is equal to 0. It's only during diode is on. When D is on, then ID is equal to 0 when omega t is greater than theta and less than 2 pi plus alpha, and equal to IC plus IR when omega t is greater than 2 pi plus alpha and less than 2 pi plus theta. So I will add the two currents, 0, and here it will be C omega V maximum cosine omega t plus V maximum over R sine omega t. This is the source and the diode current. And to find the peak value of the diode current, which is important to select the diode characteristic for the circuit, it will be C omega V maximum, and it happens at cosine 2 pi plus alpha. this is the maximum value at which the diode current will be maximum, plus V maximum over R sine 2 pi plus alpha. And we can look at the graph. The diode current will be on till the capacitors till the diode is turned off and the capacitors start to discharge through the resistor, and then it will continue in this way. So this is the peak value of the diode current. I diode peak is equal to, take V maximum out, and then it will be C omega cosine alpha plus 1 over R sine alpha. So this is the how to calculate the peak value of the diode current. Now to find the peak-to-peak ripple, which is, as we said, that the output voltage will act like that, then there will be a maximum and a minimum voltage, so the difference between them is called delta V out, which is the peak-to-peak ripple, and it will be V output max minus V output min, and delta V output max is simply the maximum voltage minus V maximum voltage multiplied by sine alpha. Since this is alpha, so sine alpha multiplied by the maximum voltage, it will gives me the minimum voltage here. So I will take V maximum as a common factor. It will be 1 minus sine alpha. So alpha also can be found by using this equation, sine inverse 1 minus delta V out over V maximum. Some application, the peak-to-peak ripple is determined or is given, and they want us to select the cap that achieve this peak-to-peak ripple voltage. So how can we find that? If omega RC is much greater than 0, then alpha it will be pi over 2 on the other side, and theta is equal to pi over 2 on the positive side, just before 90 degree, and this is just after the 90 degree. So we can use, instead of using this one, we can use another peak-to-peak ripple voltage, which is V maximum over the frequency multiplied by RC. So this is just when this one is very, very large. Now example, the voltage source is 120 degree volt. This is RMS. So the maximum value will be root 2 multiplied by 120. The frequency is 60 Hz. The resistor is 500 ohms. And the cap is 100 microfarad. So find an expression for the output voltage. We just proved that the output voltage as a function of omega t is equal to V maximum sine theta E minus omega t minus theta over omega RC, and also V maximum sine omega t. This is when omega t is greater than 2 pi plus alpha and less than 2 pi plus theta. And here when omega t is greater than 2 pi plus theta and less than 2 pi plus alpha. So first we find theta, which is pi minus tan inverse. Omega is 377 multiplied by 500 multiplied by 100 micro over 10 to the power 6 because of the micro. So we get 93 degrees. So the output voltage will give me 120 root 2 sine 93 degrees E minus 377t minus theta, which is 93 degrees, divided by 18.85 degrees, and here it's 169.7 sine 377t. Now to find the peak-to-peak voltage, so delta V out, we said it's equal to V maximum 1 minus sine alpha. So first we have to find alpha, and alpha can be found by this equation: sine alpha minus sine theta E minus 2 pi plus alpha minus theta over omega RC, and we make it equal to 0. Then we use the, for example, Texas Instrument calculator, wherever is it, 89 or 84, and we find that alpha is equal to 48 degrees. So now we find the peak-to-peak voltage, which is 169.7 multiplied by 1 minus sine 48 degrees, and it gives us 43 volts. So the peak-to-peak ripple voltage is 43 volt, which is quite high. C, we have to find the capacitor current. To find the capacitor current, we simply plugged in the numbers. IC as a function of omega t is equal to minus V maximum over R sine theta E minus omega t minus theta over RC R omega C, and here it's omega C V maximum cosine omega t. Then IC as a function of omega t is equal to minus 0.339 E minus omega t minus 1.62 radian divided by 18.85, and here 6.4 cosine omega t, which is 377t. Then in D, we have been asked to find the peak current that is flowing through the diode, and this is very important to select the diode characteristic. So ID peak is equal to V maximum cosine alpha C omega cosine alpha plus sine alpha over R. So it's 169.7, and here it's 100 multiplied by 10 to the power minus 6 multiplied by 377 cosine 48 plus sine 48 over 500, and this will gives me 4.5 ampere. Now he asked to find the peak-to-peak ripple voltage. He asked to find the capacitor that will make the peak-to-peak ripple is 10% or 0.1 V maximum. So I assumed that the omega RC is much greater than 1. So delta V maximum, V output is equal to V maximum over FRC. So C will equal to V maximum over F multiplied by R multiplied by the peak-to-peak ripple, and this turned to be 3.33 millifarads. So I selected 4 millifarads. Then if I'm asked to find alpha, it will be equal to sine inverse 1 minus delta V out over Vm, and it gives me 81.9 degrees, and the peak current is 30.4 amps. And we can see that whenever we reduce the peak-to-peak ripple, the peak current on the diode will increase, and this will make much stress on the diode, so we have to select more expensive diode. So we have always to compromise between the peak-to-peak ripple and the diode peak current according to the price of the diode and the size of the diode as well. Thank you very much, and I appreciate your time for watching my lectures.